name is Blok. Thank you for the introduction, Ian. I'm going to talk about this project, which is part of the Additive project. It's basically short fibers, using them for continuous fiber performance. So I'll talk a little bit about that. And we're going to talk a bit about composite manufacture, mainly 3D printing. Some people call this Composites 2.0, maybe 3.0 would be better. But I'm going to talk a bit about the good stuff and the bad stuff and how I would like to improve this. So a brief outline, well, I'll talk about the current and what I think I can do to improve 3D printing of composite materials. I'm developing my own filament, so I'm going to talk a little bit about this Additive project, making thermoplastic preforms and then making filament. And then lastly, future work, so what can you expect when you come back to the CD conference next year. So, additive manufacturing. Why look at additive manufacturing for composites? We all know composite materials are laminates, built up like layers by layers, so can we use a simple desktop 3D printer to also build up our layers? And we bypass the use of an autoclave or presses and basically composites for the masses. And we pre-embed the fibers into our thermoplastic filament. This idea is not new, it has been done. One part is printing of microfibers. These are very short fibers, 0.1 millimeter long. Get a bit higher stiffness and strength than traditional 3D printing materials. But the fibers are too short, so they pull out, so you don't reach your full fiber strength. Then on the other hand, there are people that are printing with continuous fibers. So you get a stiffness and strength which is in the order of magnitude of what we'd expect of a continuous fiber laminate. But what you can see at the left photo here for the continuous fiber one, continuous fiber can't bend and already, so you get voids in your part which reduce the mechanical properties. So what's in between? And that's what we thought and where we might be able to improve it. What we need is fibers that are still discontinuous but above the critical fiber length. So then if we pull on them, they do reach their full strength. And this kind of a nice image to get in your head, where on one hand you have processing and on the other hand performance. If we increase the length of our short fibers, we basically increase the performance, but the processing, because they're short fibers, still stays quite good. That's the idea. Easier said than done. These are the 4 main steps for the development of the filament. So we start with random fibers and use the Additive machine to align them. We've got a little model at a poster, so if after this presentation you come around and you can see it. Then we add our thermoplastic matrix. I need to shape that into a uniform filament, and then I can print cool stuff. So let's go over each step. So this is the schematic of the Additive machine. You spray fibers in a water suspension against plates. Through the momentum change and the drop, they fall, they align, they fall on the conveyor belt, and then you have vacuum underneath and you end up with a dry fiber preform. They had the epoxy matrix in the original study. You got the continuous fiber properties, as you can see here, and this process is also really suitable for recycling. I won't go into much detail because you get a presentation later by Restepper about that. The next step for me is add a thermoplastic matrix. So I looked at PLA, nylon, ABS and PETG as my matrices, and I did an initial study of what kind of mechanical properties can we expect. Now this is for a fiber form fraction of 12%, which is still quite low, but it's an initial study with prototyping. And we had already see quite a good increase in stiffness, especially a high strength. We do reach full strength of our fibers, which SEM photos also show if you come later to my poster. I try to lure you in, yes. Then the next step for me is this is a rectangular preform, can't print with that, so I need to shape it into a circular filament. And this is where I devised a custom contraction block with a glass plate to track the fiber alignment. These are a few pictures, but I've got a video of it, and this is what I'm doing at the moment. So here you see the filament going through, and because the fibers are aligned, initially they increase alignment, but I'll play it again, because at the end you see it's not completely working yet. It starts off quite good, but then at the top you see, I think it melts, the heat goes up, the filament melts at the top, and there it gets weaker and then it just goes down. So this is a process I'm optimizing at the moment. But once I've done that, I can print really cool things. I'm interested what you would print, ranging from medical applications, aerospace applications, and the coolest, of course, my favorite home applications, also very handy. So the future work, more on the serious side. We've got kind of a proof of concept now, so I'm going to study the rheological behavior and then use a particle-based method to track the fiber alignment. So that's what I'm working on. If you have any questions, I'm happy to answer them now or maybe later at my post. Thank you.